Hello everyone and good morning after the keynote. My name is Oskar Laverny and I'm here to talk about an optimization problem that I stumbled upon in the middle of my thesis that actually forced me to use Julia. It was 2.5 years ago and since then I kept using it, of course. It's one of the reasons that I'm here. But yeah, the point of the talk is to describe you the problem and explain to you why Julia was in fact the unique possible solution to this problem. So I'm going to start by describing the problem itself. I'll propose an algorithm to solve it, and then from this algorithm we'll discuss the whys and the hows of the need for Julia. So the problem is actually quite simple. There are a lot of equations on the screen, but it's not that complicated. There is a class of distributions, which is called the Thorin class of gamma convolutions, and which is simply defined by their cumulative generating function as follows. This class of distribution is actually representable as a risk factor structure on the bottom of the slide, and it's the distribution of the random vector x that is defined as a matrix vector product where the s's in the matrix are parameters and the g's are independent gamma random variable which all have shapes alphas that are also parameters. And so the problem is a parametric estimation problem, right? We have observations from the random vector x and we want to find the set of parameters alpha and s's that corresponds to these observations. It's quite a classical problem. The issue is that we have no density. The model is defined in the complex space from its moment generating function m and its cumulative generating function k, which is simply the log of m. And when we started working on this class of distributions in 2020, there were no estimation procedure available. It's probably because of the deconvolution nature of the problem. In fact, it's a hard numerical problem. So the first thing that we proposed is to tackle the problem by using a loss that is a projection of the squared loss on the densities into a given orthonormal basis of L2 of R plus D. The basis is simply the Laguerre basis. This is the orthonormal basis that is associated to gamma distributions, so it's quite natural to use this one. I won't bother you a lot about the definition of the basis itself. But if the density of the random vector f is square integrable, then we can project it into the basis and we obtain a set of coefficients AP that are simply defined as the integral of phi against the density, which is explicited there. And so there is a bunch of combinatorial stuff here, and here there are things that are in fact the derivative of the moment generating function taken at a point -1. And this provides a loss, which is the approximation of the squared error between the true density and the estimated density from the data into the basis. So we are first to truncate the basis, of course. I won't bother you about the justification of the truncation, the exponential decaying of the coefficients and blah blah blah. But there are some coefficients AK hat that we estimate through Monte Carlo from the data. That's the easy part. And there are some coefficient AK of alpha S, which we need to compute from the parameters to be able to compute the loss and fit the parameters. This is the problematic part. To compute these coefficients, we have an algorithm that I won't describe you completely, but basically what it does is that it computes the derivative of the cumulative generating function, and then through a Faddeeville formula, the derivative of the moment generating function, the mu's, and then through this combinatorial equation, it computes the Laguerre coefficients, and then it returns the loss in the bottom. This algorithm is pretty fast. That's actually, we can actually prove that it's the fastest possible, but it has a lot of flaws. So let's try to understand what are the flaws of this algorithm. The first one is that it's full of factorials and binomial coefficients. That's a huge problem because it will overflow. I promise you it will overflow. Yeah, there are basically factorials and binomials on every line, right? So that's a problem. The second problem is that it's fully recursive and each line depends on all the previous line. So it's completely linear. You cannot parallelize it at all. That's also problematic because it will require performance computations and probably compiled code to be able to achieve some kind of performance. And the last problem is that the loss that we produce is not convex, but not convex at all. It's actually a dense polynomial into some transformation of the parameters. It has a lot of local minimas, and what we want is the global minima, of course. But to found it, we need to use some heuristics and some global minimization routines, and this is also not a very good found, right? So 3 problems. The first one is that the algorithm is full of combinatorial stuff, and so we probably require some arbitrary precision computations. The second one is that it's highly recursive. It cannot be parallelized, and therefore to avoid spending too much time, we probably need to compile stuff. And the third one is that it's highly non-convex, and so we require some global optimization routines. The arbitrary precision computation can be done in many languages, usually through a wrapper of the MPFR, which is the base one. The big floats in Julia are just a wrapper of the C MPFR. This is also available in R, in Python, in MATLAB, and in a lot of languages, so that's not a problem. The global optimization routines are also available in a lot of languages. There are particle swarms, for example, in Julia, in C++, in R. And compilation can also be done in a lot of languages through just-in-time compilations, or even beforehand if you have a language that supports it. But global optimization routines that works in arbitrary precisions, that's something that is only available in Julia. That's something that doesn't exist everywhere else, unless you recode the global optimization library to handle big floats, which will take 10 person and a year of work, which I don't have as a PhD. Unless you recode the arbitrary precision library, which will also take a lot of work, and I can't do that. And so I learned Julia. It was the easiest way to solve the problem. To give you some numbers, on a quite standard example for what I had to do, if I compute stuff in float 64, to compute the loss, it takes 0.12 of a second, but the error is of the order 10 to the hundreds, and so that's not very good. This is the combinatorial stuff that are producing basically noise, and so we are trying to minimize noise, which is not very useful. And we have to go down and to increase the precision. If we go to big float, which is 256 digits of precision, in base 2, I think. We got the correct loss, which is of the order 10 to the minus 8. And in fact, if we go into multi-floats, we need to go to 5 times the precision of float 64 to have the correct loss and to be able to work and actually to minimize what we want to do. And voila, this thing has been the subject of a discourse thread 2 years ago that is still there, and on which we discussed a lot about what will be the right implementation. And there is also a final code on some package that is not registered at all. It's just I stored it there because I needed to keep it somewhere. Voila, thank you very much. If you have questions, I'm over here. Yeah.
Use the microphone if you have questions.
Oh.
There you go.
Thank you. So probably naive question, but whenever I run into the combinatorial stuff and the vectorials, I log transform it, and I can work with float 64s and things like that for my use cases. I assume maybe that's not feasible here.
Yes, it's not. It's not feasible because what we have, maybe it's, on this one. What we have basically is we already log transformed it. The log transformation is the fact that we compute the kappas there, which are the derivative of the log. And then to unlog transform it, we have to apply the Faddy-Barrow formula to get the derivative of the exponential of k, to get the derivative of m. And this is the combinatorial stuff. So it's already what we did, but to get back from it, you still need to apply some combinatorial mechanisms. Okay, so thank you.